Good morning. Welcome to today's doctoral meeting. We have the pleasure today of welcoming Manuel Bendaña Gómez, who's doing his PhD in computer vision. He's been working on his PhD for about 1.5 years now. And well, he's had some publications, and we'll be talking about all of that today. Well, his supervisors are Professors Manuel Mucientes, who's here with us today, and Víctor Brea. And his PhD is funded by the Spanish Ministry. You know, the competitive funding FPU fellowship, if you know the Spanish system. So Manuel has a degree in computer engineering from USC and a master's in computer vision. It's the joint master's with Portugal, with Porto. And well, he's kind of always worked on computer vision subjects, not just multi-object tracking, which is the topic today, but also object detection and segmentation. Prior to his PhD, Manuel worked at CiTIUS actually for his bachelor's thesis and summer internship. And also for his master's, he was funded by the Junior Research Staff Program at USC. And today he's going to talk about segmentation-guided association refinement in multiple object tracking. So you have 20 minutes, and then there will be some time for questions. Thank you.
Thank you so much for the introduction. Good morning, everyone. Thank you for coming. And I'm going to begin this presentation of this work that I've been doing during the last months of my PhD, which is centered on the multiple object tracking problem. So let's begin describing this, the motivation of this work. Multiple object tracking consists on the location of all the objects that are present through the different frames of a certain video and in preserving all their identities over time. So a problem like this can be solved in different ways, and one of the most common and also one of the most successful ones is tracking by detection, in which the idea is the one shown in this slide. Having a certain frame of the video in which we want to perform the tracking, a detector is in charge of identifying all the objects that are present in the frame, which we name detections, and these detections are matched with the objects that were present in the previous frame that we normally refer to them as tracks, through a data association step. So as a result of this data association, we will have three kinds of outputs. One of them are the set of matchings between detections and tracks, in which we will normally use the detections to propagate the tracks to the current frame. We will have also a set of unmatched detections, in which we will use them to initialize new tracks, new objects that are appearing on the scene. And then we will have a set of unmatched tracks that normally, in a conventional tracking by detection pipeline, they will be considered as lost. Here in the right part, we can see a simple example of how the association works. We have the set of objects from the previous frame and the set of detections from the current frame, and we match them, we compute the similarities between them using a metric like the intersection over union, typically used. And having all the similarities, we solve the assignment problem through methods like the Hungarian algorithm that is normally used. So a problem with this pipeline is that among this set of lost tracks, we normally have objects that are considered as lost, but really they are still present on each of the on that frame. So this problem is common when the detector fails and we don't have a detection for those objects that matches with that track. So in that case, the object is lost, but it is still present. This is common in situations with occlusions. So in our work, we have tried to address this problem, and one direct way that we could think for solving this problem would be to use a visual object tracker, that is a model that takes into account the last position that we have available for a certain unmatched object and the frame in which we want to locate it, and if it is still present, this visual object tracker will provide us the position of the object in that frame. But the problem of this is that this is based on bounding boxes. And a problem with bounding boxes, especially in this kind of occlusion situations that I have commented before, is that they can contain information from other objects inside. You can see here this example in which we have two objects, and object number one has a bounding box which contains a lot of information from other object, object 2, And a more precise way of solving this, because with this can complicate the things for preserving each of the tracking of each of the objects, would be to use segmentation masks. A mask identifies in which specific pixels each of the objects is present, being therefore more precise. And having this idea in mind, what we do in the work that I'm presenting to you today is to propose a new mod system that we name Segmentation-Guided Association Refinement in Multiple Object Tracking, SGAR mod, which is basically an extension of a conventional tracking by detection pipeline. In our case, we have chosen a state-of-the-art tracker, which name is by track. And we add to that tracking by detection pipeline a new module that is in charge of managing that set of lost tracks that may be lost due to failures on the detector. This module is named Object Recovery Protocol and is based on these segmentation masks. So we are going to see all of this in detail, but first of all, I will show you the general pipeline of the SGAR mod system that we have proposed. So here you have again the tracking by detection idea, but now you can look here to this set of unmatched tracks, and they are going to, instead of being considered lost, enter into the Object Recovery Protocol module that I have commented before, in which we will have two kinds of outputs: a set of recovered tracks that we will add to the full set of tracks in that frame, and also a set of non-recovered tracks that will remain as lost. Here we should have objects that should in fact be lost in each of the frames. So let's enter into this Object Recovery Protocol, and the first thing here is to say that we have four main stages inside it. As it is based on segmentation masks, the first stage is to extract masks for each target object. Then each of these masks will be pre-processed through a mask pre-processing stage. And the idea here is to feed a set of masks onto a Vision transformed network. That name is Mask Instant Resolver, that is over here. This Mask Instant Resolver will help us in the decision-making process, and it will provide us basically a probability final value that we will use in the last step, that is the decision-making. And with that, we will decide to recover each lost track. So let's begin with more detail in each of the stages. We will begin, of course, with the mask extraction, which is the first step. And here the idea is to use a segmentation model. In our case, we have chosen a well-known segmentation model from the state-of-the-art, which name is Segment Anything Model, abbreviated as SAM. And in particular, we have chosen its second version, SAM2, which has some novelties with respect to its predecessor that were interesting for our case. So one of them is that we can perform here video segmentation. We can provide information about a certain object in any frame that we want. In this case, we will provide information about the object in the last frame in which we know is present, in the previous frame. And this information can be either a bounding box or a segmentation mask, if we have gone through this process through this module in the previous frames as well. And with this information, we can generate segmentation masks in the posterior frames of the beam. We also can provide information about the neighborhood, and this is very interesting. We can indicate SAM2 to avoid generating overlapping segmentation masks. So the idea here is to try to get a more precise output, making SAM2 aware of the spatial context that is surrounding each target track. So with this, we can generate multiple segmentation masks for each target object. And one question that would arise here would be, how many masks do we need and why? So as I commented before, the idea is to provide a set of masks to a Vision transform based network, the Mask Instant Resolver. And the idea of this Mask Instant Resolver is to take 3 masks from the target object from 3 different time steps. And it will provide us the probability of those 3 masks to belong to the target track and to be correct. So these 3 masks are the following ones. The mask from the current frame, which represents the latest prediction that we have made for this object, and where we want to know that the object is still present or not. The mask from the previous frame, in which we know the object was still present. And apart from these 2 that are probably the most obvious, we have the mask from a frame that we named the detection frame. It is this one. And what is this detection frame? The detection frame represents a situation in the video in which the object was being tracked with, was being associated basically with detection in the normal tracking by detection pipeline. So it should be a situation in which the object is less occluded than in the latest frames. So we will provide these three inputs to the mask instant resolver, but we don't give the masks directly to the module. Instead, we apply first a mask preprocessing step. The idea of this mask preprocessing is to use the same idea that is used inside the SEM2 model to preprocess any segmentation mask that is given as a prompt to this model. So firstly, a resizing over each mask is applied to a size of 256 times 256. After that, we go on to a prompt encoder, that is the same prompt encoder that SEM2 has. And with this, we will get some output embedding of a fixed size. In parallel, for each frame in which each of the masks was generated, we will run the image encoder, also from SEM2, from which we will get an embedding of the same size than the one given by the prompt encoder. So we will combine the embeddings from each segmentation mask with the embeddings of the corresponding frame in which the mask was located. And after that, we will get the final embeddings that will be provided to this mask instant resolver, to this MIR module. So let's enter into the details of the MIR module. The first thing here is to perform a flattening of each of the embeddings and a linear projection that will convert them to a fixed input size for our transformer. And in parallel, we will compute positional embeddings for each of these embeddings. These positional embeddings are computed taking into account, in each case, the spatial position of each mask, the spatial scale of each mask, and also the temporal distance. So combining this information, we get the final input embedding that is provided to a common vision transform-based encoder that gives us an output embedding of the same size. So in order to get that final probability value that I have commented before, we provide this output embedding to a multi-layer perceptron that gives us this value. With this, we go to the decision-making process, in which basically we check if that value is over a certain threshold. In practice, this threshold will be set to 0.5, and if that's the case, we will consider that the object should be recovered, and if not, it will remain as lost, as it was going to be without this module. Something important before finishing with this description is that this object recovery protocol is based on segmentation masks, but the complete tracking by detection pipeline is still based on bounding boxes. Therefore, we need to keep a bounding box of each of the objects that we recover here. For that, basically, we take the bounding box from the previous frame and we displace it to the current frame, taking into account the displacement produced between the segmentation masks of the previous and the estimated for the current frame. So now we will show some of the results that we have achieved with this SGARMOD module. And first of all, we will comment here the data sets that we have used in the experimentation and also in the implementation of the different components. First, we have used MOD20 dataset, which is a very common dataset of people that contains situations with lots of occlusions and also with people crossing each other. It's a quite complex dataset. We have also VisDrone, which is a dataset, an aerial dataset containing both people and vehicles. We have Sports Mode, which is another people dataset, but in this case in sports scenes. So in these situations, we normally have similar appearances between the different persons, and also we have irregular motion. We can have a person running in one direction and due to a sudden change on the game, change to the opposite direction. So it has its complexity as well. And apart from these three that were used in the evaluation, we have ModSynth. ModSynth is a synthetic dataset which was very interesting for our case because it contained a lot of videos and all of them annotated for every people that was present in each of the frames. And it has annotations of both bounding boxes and segmentation masks. So this was really useful in order to perform the training of the mask instant resolver network that I have shown you before. It has no test set. So in the experimentation that we are going to show here, we are going to focus on these three datasets that they have a proper testing set for evaluations. So I'm going to show you two comparisons. First of all, we will focus on comparing our SGAR mod with our baseline by track method, and then we will extend the comparison to more state-of-the-art trackers. So if we focus on the comparison with the baseline, which is the most direct comparison that we have, you can see how we are reducing this column of the false negatives. We are, of course, recovering objects from being lost that shouldn't be lost, so we are reducing this number considerably, and also we are introducing some false positives, which is normal because we are also sometimes recovering objects that shouldn't be recovered. But if we take into account the combination of false negatives and false positives, which represents the total number of errors, you can see that globally they are reduced, as the reduction on false negatives is larger than the increase in false positives. We also reduce in some cases, like in the case of a sports mode dataset, the number of identity switches. What does that mean? We are preventing some objects from being lost for a certain number of frames, and then recovered, re-identified with a new detection, with a new identity. So these kind of reductions are helpful in order to improve the performance in different metrics that are normally used to assess the mod system's performance. The most relevant one, and the normally used in the different articles to compare to the state of the art, is multiple object tracking accuracy, which we are improving on all three data sets. And we also are able to improve, in the case of a sports mode and BISDRON, other metrics that are common, like higher object tracking accuracy and identity F1 score. If we extend this to the state of the art, we have chosen a set of 6 methods from the state of the art in all three data sets, and we have ensured as well that they were tracking by detection based methods, and also we have ensured that they all use the same detector, just for fairness in the comparison. So in this case, we are able to rank among the top 3 performing methods in all the data sets, and in the case of BISDRON, our method is able to get the best results. Something interesting about BISDRON dataset is that it's not that widely used in comparisons with the state-of-the-art in our other articles from other methods that we are showing here. And this is interesting, for example, to see in the case of hybrid sort, which is a method that is able to be among the top performers in the other 2 data sets, but in the case of BISDRON, is getting the worst result with a negative MOTA score. Negative MOTA scores can appear when the number of errors that that method is taking is too large. So basically, hybrid sort is not able to handle the set of detections that is provided by our detector. So if we take into account the overall performance in all the data sets for all the methods, we can see how our method is the most consistent one, as it achieves the highest average performance, followed by the previously mentioned hybrid sort and by our baseline by track, which was already on the state of the art. In any case, the most important here is that we are able to consistently improve our baseline, and at the same time we are competitive in the state of the art comparison. So in conclusion, basically we have introduced here in this presentation our latest work, SGAR mod, which is based on the tracking by detection standard pipeline idea, adding our object recovery protocol, which works with unmatched tracks, trying to recover lost tracks that shouldn't be lost in each of the frames of the video. This object recovery protocol is based on segmentation masks, and it contains the use of SEM2 for mask generation, and also our mask instant resolver trained network in order to help in the decision-making process. The results confirm how we are able to improve our baseline method that was by track, and how we are able to be competitive with the state of the art. So now I will talk in the last minutes about future work that we are considering now that we have finished with this work. One potential option in which we could focus would be to taking into account that segmentation masks were useful in our case to recover lost objects that shouldn't be lost. We could directly remove this object recovery protocol and perform a data association purely mask-based. So this would be moving towards a tracking by segmentation approach instead of tracking by detection. Another potential option would be to do a generalization of the multiple object tracking problem to other different scenarios like open vocabulary. We are used to, in multiple object tracking, to work with a closed set of categories, like you can see in the picture, person or car. So the idea here would be to generalize to a wider set of categories, even including categories that are not seen in the training step. So this would be something that is closer to a real-life scenario in which we can find objects that we have never seen before, and would be also an interesting potential open line of work. And the last one would be to check the results in that we get in the state of the art, and check if there were data sets with some margin for improvements. And this happened in the case of the Bistron data set. This is the output of our tracker. That's the ground truth output. And as you can see here, there is a region of cars that are not being identified. This may happen due to mainly two reasons. One of them would be that the detector is not able to identify this kind of objects. And the other one would be that it is able to identify them, but with such a low confidence value that we are filtering them from the association step. So some work could be done in order to try to get these objects onto the tracking process and, in the end, improve the performance on this data set. And that will be everything from my side. Thank you for your attention, and I will be happy to answer any of your questions.
Yeah, so thank you for this great talk. Do you have questions? There were questions.
Thank you for your talk. That was awesome. My question is about the threshold that you set for detecting or not detecting, or recovering or not recovering an object. Is there ever a case where you'd want to adjust that threshold to make it higher or lower? And what would a scenario that required that look like?
Yeah, I mean, basically this came from the training process of the mass instant resolver that I didn't enter into those details here because there were specific details. After the training process, we checked how the performance was, and we have seen how with 0.5 it was the best result that we have achieved. We had a selection of that ModSyn dataset, which didn't have a test set, but we reserved certain videos for doing validations, and there we checked the performance that we have with different threshold values. So yeah, there 0.5 was the best option, and that was in practice the value we selected. But yeah, we considered that possibility of maybe with 0.6 it was better, because with 0.5 we are accepting some false positives, for example, but it was not the case.
Great, thank you.
There was another question here.
Hey, thank you, Manu. Very nice talk.
Thank you.
So I'm curious about the SAM2, this mechanism used to generate the mask. So I guess there was a SAM1.
Yeah.
So can you comment how did you compare, or are they both yours, or?
Sorry?
Are they SAM1 and SAM2? I guess they are yours.
No.
No?
They are from the state of the art.
Okay.
Yeah.
Okay, so anyway, can you comment the
I
differences?
mean, if we have tested SAM2 and SAM1, you mean? Yeah, I mean, there was prior work to this, using instead of this second version, the original one. I commented some novelties that were useful for us, specifically for this case. In the original SAM, we couldn't do video segmentation, and we couldn't indicate to avoid overlapping between segmentation masks in the output. So the only way that we had here were to provide bounding boxes as a prompt, but bounding boxes, if, as I have commented before, if they contain information from multiple objects and we want to generate segmentation masks, are not that precise also if we provide them as a prompt. So we had some approach here based on using points as a prompt instead of boxes, points that were located inside that bounding box, and basically there we generated multiple segmentation masks, and we had a network similar to MIR but a bit more complex in the number of inputs, which basically selected one of the masks if it was correct for that object, for each object. So it was a prior work with which we get some improvements also with respect to by track, but improvements were not that large, and in that moment we weren't considering all the data sets like right now. We were considering the first one, mod 20. And basically in that moment, SEM2 appeared, and we said, okay, maybe it's worth to check what is going on here and what possibilities it offers to us. And in the end, it was the best option. But yeah, we had some exploration with the other method. But both are from the state of the art and from different articles.
Thank you.
Thank you, Manu. Very nice talk. I am just curious about the third dataset that you used to validate, the one from sports events. Yeah, exactly that example about football. In the situation we have many people with the same clothes, no, with the same kit. Is it really a challenge to track these people, to keep the identity of these people, for example, in cases like the corner kicks where there are all together, in this case, I don't know, 10 people with the same clothes? How does the model perform here, and if it is really a challenge, and how do you face it?
Well, in the case of, thanks for the question, in the case of sports mod, I don't know, here I have the comparisons. The MOTA score is really high, even in by track, and we are also helping to improve it a bit more. It is true that it's challenging, for example, in that situation that you explained. There are scenes from also different sports, not only football, it is volleyball, I think there is basketball and so on. But in any case, yeah, there are complex situations like this. And it would be a challenge because the segmentation model there would see people with the same appearances, with the same kit. But in any case, we are still able to reduce this number, which was the most relevant thing. And you have also to take into account that we are recovering maybe some of the objects, not all of them. Maybe some of them are still tracked through the normal tracking by detection pipeline. We provide them to the segmentation model, and it is able to distinguish them by providing each individual bounding box. So yeah, in the end, you can see how we are able to manage also with this data set despite that thing.
Okay, thank you.
Thank you. So, other questions? Well, maybe I can ask one then. For people who are not familiar with computer vision, like myself, so what are some of the downstream applications that could benefit from improved multi-object tracking?
Well, there are some applications that we could think of, for example, in autonomous driving, for identifying people on the road, for example. It would be a possibility. Also for video surveillance applications that we could think of, surveillance cameras. Or, for example, we had some applications like you could have a drone with a camera and search for people in some places in which maybe they are lost, or you want to keep them tracked and you want the identity of each of the people to maintain them identified correctly. So that will be some examples in which it would be useful.
Okay, thank you. Since I work with language, do you think this could be useful for audio description? You know, audio description, when it generates audio description for accessibility.
Yeah.
Do you think this could be factored in, and then the descriptions would be better because the identity?
But what do you mean exactly? Do you mean to generate an audio description about?
To improve, yeah, or to improve it, yeah.
Well, it would be a possibility to use different modalities to also assess these kind of problems. But of course, for that, you will need data sets and data for that kind of work. But yeah, I think it will be also a possibility. It will be interesting, yeah.
Okay, thank you.
But sometimes in these cases, we lack of that specific data to perform that kind of applications.
Okay, great. So, no other questions in the meantime? Well, then maybe, yeah, we can leave it here. Thanks a lot for a great talk and good questions.
Thank you so much.